There's this running joke in the world of physics.
Yo, I think I know where you're going with this.
Fusion energy is always 30 years away, and room temperature superconductivity,
Always just around the corner.
exactly. It's filed in the same cabinet. It's the holy grail. I mean, just imagine a power grid that loses absolutely zero energy.
Or MRI machines you could fit in a backpack. No more giant tanks of liquid helium.
It sounds like science fiction.
Sounds like Star Trek.
It does. And for decades, the way we've hunted for this is, well, honestly, it's basically just high-tech cooking.
Right. You mix some elements, bake them at insane pressures, you freeze them, and you hope for a miracle.
It's trial and error on a massive scale, but I've got a paper in front of me today that says, well, that we might be doing it all wrong.
That's a bold claim, but sometimes you need one of those to break a deadlock.
The source for this deep dive is titled Electron Tunnel by Jerry Z. Liu, and the premise is simple, but kind of revolutionary. Stop trying to discover superconductors like you're panning for gold.
And start engineering them, like you're building a bridge.
Exactly.
Right. So Liu's proposing a new theoretical framework here, one that tries to unify how we look at everything. Insulators, conductors, superconductors. He's arguing they're not totally different animals.
They're just different points on the same spectrum.
And if you understand the spectrum, you can actually manipulate it.
And to get there, we have to get our heads around his core metaphor. He says we need to stop picturing electricity as this, sea of electrons just sloshing around.
Instead, he wants us to look at the structure. He compares a conductor to concrete.
Concrete.
That's a really helpful visual. You've got the stones, the aggregate, and then you have the cement that binds them all together.
Right.
In his model, the stones are these isolated spaces around individual molecules. He calls them isolated cells.
And the cement.
That's the electron tunnel. It's a network of paths that runs between those cells.
So the whole argument is that electrons don't just flow anywhere they want.
They're not free agents. They have to get into that specific tunnel to move.
Okay, so let's break that down, because when I think of a copper wire, I just picture a highway where electrons are zooming along.
Well, this theory suggests there's an entry fee to get on that highway.
An admission price.
Yeah. Think of an electron in its natural state, orbiting a molecule. It's sitting in that isolated cell. It's comfortable there.
Yeah.
It's stuck in its room.
And if it stays there, no current.
It's going nowhere. So to get it moving, you have to kick it out of the house.
You have to give it a boost.
You have to elevate it. You have to add energy to lift that electron from its home orbital up to the energy level of the electron tunnel.
Yep.
That gap, that's the admission price.
And this is where Liu sorts all matter into 3 buckets.
Exactly. It all just depends on the tunnel.
So let's start with an insulator, like rubber.
Okay, in Liu's model, for an insulator, the electron tunnel simply doesn't exist. There is no road.
It's a dead end.
A total dead end. It doesn't matter how much energy you give the electron. If there's no path between the molecules, it can't flow.
Right. What about a conductor like the copper in my walls?
So here, the tunnel exists, the road is there, but it sits at a higher energy level than where the electrons are naturally living.
So the electrons are living in the basement, but the highway is on the 2nd floor.
That's a perfect analogy. To get traffic moving, you have to pay energy to lift them up to that 2nd floor. That effort is what we feel is resistance. We'll get to that.
Okay, which brings us to the main event, the superconductor.
In a superconductor, the geometry shifts. The theory says that the valence orbitals, basically the electron's living room, they intersect directly with the electron tunnel.
So the basement's gone, the house is built right on the highway on-ramp.
It is. The electron can create a current without needing that energy boost. It just flows effortlessly because it's already at the right level.
And Liu makes a point to say this isn't just regular band theory with a new name.
Right, he's very clear on that. We usually hear about conduction bands, which are more abstract. The electron tunnel is focused on the actual spatial connectivity, the physical road the electron travels on.
So if the tunnel is the road, what builds it? Why does copper have one and glass doesn't?
That brings us to the master key. This variable he introduces, called $, the attraction coefficient.
Right. And this is all about how much your neighbors want to hang out.
I mean, essentially, yeah. It measures the intensity of attraction an electron feels from the molecule next door. It's a scale from 0 to 1.
So if C is 0,
your neighbor is ignoring you. No attraction, you're totally isolated.
no tunnel forms, you're an insulator.
Exactly. But as CDS goes up, the neighbor's influence grows. If CDA hits 1, it's like the neighbor has a vacancy in an electron hole. that's pulling you in with maximum force.
There's this conduction zone graph in the source that really visualizes
It's
this.
a great graph. When the attraction is strong, so C equals 1, the energy curve dips down and creates a really wide tunnel. Think of it as a 6-lane superhighway.
Easy flow. But as that attraction drops,
The tunnel narrows. At C or equals, say, 1/3, the road gets tight. It's harder for electrons to squeeze through.
is there a point where the road just collapses?
There is, and the paper is very specific about it. The magic number is roughly 0.225.
That's really precise.
It's the tipping point. If the attraction drops below that, the tunnel disconnects, the path vanishes,
Yeah.
and the material snaps right back to being an insulator.
So the whole game is keeping C or dollar above that line.
And ideally, as close to one as you can get it.
This also seems to explain resistance in a way that just clicks. I mean, we know resistance creates heat. It's why my laptop is burning my lap right now.
Right. Lou frames it all around that jump we talked about.
From the basement to the highway.
Exactly. You spend energy to lift the electron up there. But electrons are unstable at that higher energy level. They don't want to stay.
They want to go back home.
They're constantly looking for an opportunity to fall back down into an empty spot, an electron hole in a lower orbital.
And energy can't be destroyed, so when they fall,
They have to release that potential energy you gave them. They dump it as photons.
and that's the heat.
That's the heat. It's the sound of millions of electrons falling off the highway.
So for a superconductor,
The orbitals overlap with the tunnel, remember. There is no up. There was no lift.
so there's no fall.
Precisely.
Hmm.
Since they never had to be lifted, they have no potential energy to lose. They just slide across at ground level. No fall, no photons.
No heat. Zero resistance.
Frictionless motion. But, being a superconductor isn't just about electricity. It's also about magnets.
The Meissner effect.
Yeah,
The floating magnet trick.
right. When you bring a magnet near a superconductor, the electrons in that tunnel start circulating. They create their own magnetic field that's perfectly opposite to the one you're applying.
They put up a shield.
Perfect mirror, yeah. But there's a limit. The source uses some really vivid imagery here to describe what happens when that shield breaks.
The critical current density.
Yes. There are only so many electrons available to build this shield. If the external magnet gets too strong, it overpowers them. Lou describes the electron clouds being physically compressed. He calls them squashed lanterns.
That is such a weirdly specific image. Squashed lanterns.
But it fits, right? Imagine a paper lantern. If you squash it, it gets shorter. In this model, the magnetic field squashes the electron cloud perpendicular to the field.
And if you squash it too much.
The deformation physically pushes the valence electrons below the level of the electron tunnel.
Oh, I see. So the road is still there, but the car has been flattened into the ditch.
Exactly. The connection is severed. The moment those electrons are pushed below that threshold, superconductivity is instantly destroyed.
Wow. There was one other technical detail that caught my eye about the flux quantum. The paper derives the value $20, $30.
Right.
I know dollars Planck's constant and dollars is the electron charge, but why the two?
That, too, has puzzled physicists. Standard theory says it represents Cooper pairs, two electrons paired up. But Lou offers a different explanation.
It's not about electrons holding hands.
No. He argues that when an electron moves forward, it leaves a vacancy, a hole behind it. That hole effectively drifts backward.
So you have traffic moving both ways.
A simultaneous flow. Negative charge forward, positive hole backward. Lou calculates that this dual motion is what accounts for the 2E in the equation. It fits the data, but for a totally different mechanical reason.
It's interesting how he keeps coming back to structure and mechanics.
It is. And speaking of structure, nature rarely gives us these perfect crystals.
Right. Which brings us to type 2 superconductors, the messy ones.
Messy is the right word. Usually alloys. Their molecular structure is irregular, which means that attraction coefficient $, isn't the same everywhere.
So the tunnel width changes from spot to spot.
It varies wildly. You've got 6-lane highways next to dirt paths. So when a strong magnetic field hits this material, it doesn't fail all at once.
It fails in patches.
It enters what's called the mixed state. The weak regions, where the tunnel is narrow, they collapse first. They become normal conductors and let the magnetic field punch through. These are called vortices.
Like little holes in the shield.
Exactly. But the strong regions hold the line. So you get this hybrid material that's riddled with magnetic holes, but still superconducting in the solid parts.
And the paper says direction matters here too.
Because the crystals are asymmetric. Hit it from one angle, it holds up. Hit it from another, you find a weak side, and the whole thing collapses much faster. It's like directional armor.
Okay, let's pivot to the practical stuff. Pressure and temperature. Why does taking a rock and squeezing it with a diamond anvil sometimes turn it into a superconductor?
It all goes back to our friend Talon, the attraction coefficient. High pressure physically shoves the molecules closer together.
So the neighbors get closer.
And when they get closer, the attraction increases.
Yeah.
The Tauler goes up. If you squeeze hard enough, you can literally press the admission price down to zero.
And temperature. Why does getting things incredibly cold help?
Lou calls this the equivalent compression effect. Heat is vibration, right? It's movement. Excited electrons repel each other and push outward.
So heat pushes the neighbors apart.
It does. When you cool the material, the electrons calm down, they retreat a bit, and that reduces the repulsion. The molecules can settle closer. It mimics the effect of high pressure.
So cold is just a hack to fake high pressure.
In the context of the electron tunnel, yes. Both are just ways to close the gap between the electron's home and the highway.
The paper has this phase diagram that shows the transition boundary.
It's like the coastline where resistance drops to zero. All of superconductor research is just trying to move that coastline into a comfortable zone for us.
Room temperature and normal pressure.
Got
And
it.
this is where the source really delivers, the blueprint section. He basically says, stop guessing. He gives 3 specific rules for engineering a material that has this tunnel naturally.
The molecular engineering phase. Okay, rule number 1, electronegativity.
This felt like a Goldilocks rule.
It is. You have to pick your elements carefully. Pick something with high electronegativity. He uses chlorine as the bad example. And it holds its electrons in a death grip.
It won't share, no tunnel.
But if it's too low, the element is too weak to influence its neighbor. Again, no tunnel. You need elements in that middle range, strong enough to attract, but loose enough to share.
Okay, pick the right atoms. Rule number 2 is about shape. Avoid excessively complex, large compound molecules.
Keep it simple. A huge, complex molecule is like a giant boulder in the middle of your highway. It disrupts the network. You need a clear, interconnected grid.
No cul-de-sacs.
Connectivity is key.
And the third guideline seemed a bit counterintuitive. Atomic mix.
Yeah.
Combine large and small atoms.
Right. Why would you do that?
Yeah, why does size matter?
It creates irregularity, but a specific kind. If you have a perfect lattice of identical atoms, the forces are uniform. But if you mix big and small atoms, you create these irregular intermolecular fields.
You create tension.
You create local spots of high compression. Those spots can mimic that external pressure we talked about. They tighten the bonds locally, increasing the attraction and widening the tunnel right where you need it.
So the recipe is elements that aren't too greedy but aren't too weak. A simple shape so the road isn't blocked, and a mix of big and small atoms to create strong local attraction.
That's the blueprint. And the implication here is massive. Lou is saying that superconductivity isn't some magic trick, it's a standard state of matter.
Just like solid, liquid, or gas.
Exactly. We just don't see it often because we live in a low-pressure, pretty hot world. But if we follow these guidelines, we can design a material to act as if it's under high pressure, even when it's just sitting on your desk.
It really changes the whole philosophy of the search. Instead of looking for a needle in a haystack.
Just weave the needle yourself.
And if this framework holds up, I mean, if we can actually predict these such low values in design materials, we're looking at a fundamental shift in civilization.
We're talking lossless power grids, maglev trains connecting cities.
Medical imaging, quantum computing, fusion reactors, it's the bottleneck for almost every futuristic technology we dream about.
And the paper ends on that note, suggesting we had the Stone Age, the Bronze Age, the Iron Age.
And if we master the electron tunnel, the superconducting age could be next.
It's a lot to think about. Next time you plug in your phone and feel that charger getting warm.
That heat is just wasted potential waiting for a tunnel.
Let's hope we can build it soon.
A huge thank you to Jerry Z. Liu for this fascinating deep dive, and thanks to you for listening.
Keep questioning the basics.
We'll see you on the next deep dive.